Hello friends, in continuation of our topic chemical thermodynamics, we studied in yesterday's video lecture, that is vent of reaction isotherm. So for gaseous systems we saw the vent of reaction isotherm, that is delta G is equal to minus RT ln Kp plus RT ln Qp. So this equation is very important for examination point of view. So in this equation we saw how we can calculate or how uh, free energy change is related with Kp and Qp. On this equation we want to learn two important numericals, because in examination such a numerical can be asked for 2 marks. The standard free energy change for a gaseous reaction. We will see first example, that is example number 4. The standard free energy change for a gaseous reaction is 71.128 kilojoule. Calculate the equilibrium constants of a reaction at 2000 Kelvin. What they have given? They have given the value of R. What is R? R is a gas constant, and the value of R is 8.314 joule per Kelvin per mole. Okay, so here in solution we have the formula of standard change in free energy. Delta G0 is equal to minus 2.303 RT log Kp. That equation we saw in yesterday's lecture. So what is log of Kp then? Log of Kp is equal to minus delta G0 upon 2.303 RT. If you substitute the value of minus delta G0 upon 2.303 RT, then you will get minus 71,128 joule. So in numericals they have given the change in free energy, standard change in free energy. Delta G is 71.128 kilojoule. So kilojoule is converted into joule. Okay, so 71,128 upon 2.303. You just substitute the value of R, that is 8.314, and the temperature which is 2000 Kelvin. So if you solve or if you do all the calculation, then you will get minus 1.857. If you take the, now this is log of Kp is what? Minus 1.857. To convert log of Kp into Kp, you have to take the antilog of minus 1.857, which is 0.0139. So what is the value of Kp? 0.0139. So this is how we can calculate the standard free energy change for the given data. Now numericals or example number 5. Again this is the same type of numerical. The standard free energy change for a gaseous reaction is 1 into 10 raised to 5 joule. That is delta G0 is given, which is 1 into 10 raised to 5 joule. Calculate the equilibrium constant for the reaction at 673 Kelvin. What they have given again? Value of R, which is 8.314 joule per Kelvin per mole. Okay, now here we want to calculate Kp, but we have the equation delta G0, which is equal to minus 2.303 RT log Kp. Therefore log 10 to the base log to the base 10 Kp is equal to minus delta G0 upon 2.303 RT. You just substitute the value of all the given data or given term, that is delta G0 and RT, minus 1.1 into 10 raised to 5 upon 2.303 into 8.314 into 673, which is minus 7.7603. Now again this is the value of log Kp. So convert that log Kp into Kp. You have to take antilog. Kp is equal to antilog minus 7.7603, which is 1.737 into 10 raised to power minus 8. This is the value of Kp. This is how we can calculate the equilibrium constant for any chemical reactions if we have the standard free energy change of that reaction at given temperature. Now once you understand the vent of isotherm, then we will move to the next point, that is the vent of reaction isochore. In short, that vent of reaction isochore is called as variation of equilibrium constant with temperature. So how equilibrium constant will vary with temperature, that is proved by this particular concept, that is the vent of reaction isotherm. So we will see that now. The equilibrium constant of reaction remains constant at a given temperature. Obviously, the word constant is given, that means equilibrium constant of a reaction remains constant at a given temperature. Okay, for particular reaction, that is the value is fixed when temperature is given, but the equilibrium constant of this reaction changes with change in temperature. If the temperature is constant, equilibrium remains constant, but if you change, then equilibrium constant also change. The variation of equilibrium constant with pressure with temperature is given by the vent of reaction isochore. So variation of equilibrium constant with temperature is also called as vent of reaction isochore. Okay, everybody understood what is the meaning of vent of reaction isochore? Now the standard free energy change is related with equilibrium constant by the relation we saw in yesterday's lecture, that delta G0 is equal to minus RT ln Kp. Remember this equation. Dear students, if you want to remember this equation, you should write this equation or this expression in a notebook, so that with the help of writing as well as studying, it is very easy to remember any chemical equation. So best way to understand the chemical equation is to write in the notebook in 2, 3, 4 times. So standard free energy change is related with equilibrium constant by relation delta G0 is equal to minus RT ln Kp. Now differentiate equation 106 with temperature at constant pressure. Then above equation can be written as d by delta G0 upon d by T at constant pressure is equal to minus R ln Kp. Here it is constant, so there is no need to take. Okay, pressure is constant, so write P in outside the bracket with temperature. So d by delta G0 upon d by T at constant pressure is equal to R ln Kp minus RT in bracket d by ln Kp upon d by T at constant pressure. This is the equation number 107. That means right hand side you have to differentiate in both sides, right hand as well as left hand side, with temperature at constant pressure. So equation 106 convert into 107. Now multiplying equation 107 by T, we get T T at T in bracket d by delta G0 upon d by T at constant pressure is equal to minus RT ln Kp minus RT square in bracket d by ln Kp upon d by T at constant pressure. Again, if once you multiplying the equation 107 by T, we will get equation number 108. Now substituting delta G0 is equal to minus RT ln Kp. That means you have to just substitute the value of delta G0, which is minus RT ln Kp, into above 108 equation. So T in bracket d by delta G0 upon d by T at constant pressure P is equal to delta G0 minus RT square in bracket d by ln Kp upon d by T at constant pressure. Now this is called as equation number 109. The Gibbs-Helmholtz equation for particular case in which all the substances taking part in their standard states are given by relation delta G0 is equal to delta G0 is equal to delta H0 plus T in bracket d by delta G0 upon d by T at constant pressure P. So that equation we have already studied in a Gibbs-Helmholtz equation. Equation 1010 is coming from the Gibbs-Helmholtz equation. Now if you rearrange equation 110 110, then you will get equation number 111, that is T in bracket d by delta G0 upon d by T at constant pressure P is equal to delta G0 minus delta H0. Now comparing equation 109 and 111, then we can write RT square in bracket d by ln Kp upon d by T at constant pressure P is equal to delta H0, which is nothing but delta H. Since delta H does not changes appreciably with pressure, hence delta H0 in the equation can be replaced by delta H. So if you write equation 112 into 130, that is d ln Kp upon dt is equal to delta H upon RT square. So equation 113 is called as Vent-Hoff reaction isochore. Okay, everybody understood that? Again, this is very important reaction or equation for the examination point of view. So we will stop here. Very small topic which is remaining, that we will see in the next video lectures, and some numericals. Okay, bye.